Hello, everyone. My name's Jay, and my project is on simulating age-related bone loss and disc degeneration in a human lumbar spine segment. Okay, so as the title implies, my project is primarily focused on the vertebra and the disc of the spine. Specifically, I'm interested in studying vertebral fractures in the L1 and L3 segment spine. And basically, this bottom right image here kind of shows you what such fractures may look like, while the left image here shows you an example of a healthy spine segment. And those of you who are sort of unfamiliar with the terminology that I'm using, basically these main bony terms here, bony things, these are what we call the vertebra, and the blue material that sits in between these two vertebrae is what's known as the disc. And this is just sort of a top-down view of the disc here. So you have the central nucleus portion that's surrounded by a thick collagen network that's known as the annulus fibrosus. And what I mean by the L1 through L3 segment is basically something that looks like this here, where you have three vertebrae, the L1, L2, and L3 vertebrae here, as well as two discs that are sandwiched in between those three vertebrae. And the L basically just refers to the lumbar region of the spine. So if you look here, the lumbar region is basically just the lower region of your spine near your tailbone. And the numbers 1, 2, and 3 just correspond to the specific vertebra of interest. So now looking back at the actual vertebral fractures here, these are just some statistics regarding these vertebral fractures. And just from reading these, you can sort of see that, this is a pretty big problem, like not only can they lead to things like excruciating pain, poor posture, and height loss and things like that, but it's also just very financially taxing to cover up all the medical costs associated with treatment. So it's imperative that today's doctors sort of give their patients an accurate assessment of their risk of fracture. And while current models do exist, the main problem is that while current models that can do this do exist, the results that they provide aren't very accurate, as nearly around 3/4 of those who end up with vertebral fractures were not diagnosed to be at high risk using these models. So then my goal is to use other clinically obtainable information to give a more accurate assessment of one risk of fracture. So my solution to that is to first start by building a finite element model of the lumbar spine segment. And for those of you who don't know what a finite element model is, it's basically a way of basically imagine taking some random object of interest, and you can change up certain material properties of it, and you can then run simulations on it to see how changing up certain material properties and certain values like that can affect the final result. You can see how I've taken the whole spine segment here, and I've broken this down to little parts and pieces, these little brick-like shapes, these little blocks here, and I can basically change up certain values and numbers and material properties for each of these little discs, each of these little things, and run a simulation on them. So I decided to look at two specific characteristics of the spine, namely the age of the bone and the health of the disc. And basically what I'm doing here is for each condition of the disc, so like whether it's healthy or degenerated, I'm going to be looking at how the bone changes across the span of 3 decades. So I do that for the healthy case here, as well as for the degenerated case here as well. And so once I've tweaked with those factors a bit, then I'm actually going to be simulating the vertebral fractures here, meaning that I'm going to be taking this model here and compressing it to its point of failure. I'm going to be sort of compressing it to running a series of compression tests on it to see where fails and breaks. But the main point of doing that for me really is to sort of look at what specific combination of the age of the bone, the health of the disc, what specific combination of those two actually results in the greatest risk of fracture. So on to actually simulating the age-related bone loss. Basically what I'm doing here to simulate aging of the bone is I'm basically removing bone tissue. You can see how how when you compare a 6th decade to a 9th decade bone, there's much less bone tissue and bone mineral density here, compared to a 6th decade one. And these figures overall just kind of support that conclusion. As you can see, a progressive decline in bone mineral density as you age. But one important thing to sort of take away from these figures is that the bone mineral density loss is not homogeneous, meaning that the bone mineral density, the bone tissue loss is not equal throughout all parts of the bone. And in particular, you see that in the central region here, you see a greater loss of bone tissue compared to its surroundings and surfaces and edges. And you can sort of see that here as well. There's sort of less bone tissue in the central region compared to the surfaces and the edges and surroundings. Okay, so now to simulating disc degeneration. What I did was I basically looked at specific properties of the disc, and I modified them so that I modified them to see what they would look like in their degenerated state. So the first thing they looked at was something called fixed charge density, and you can basically think of fixed charge density as the disc's ability to absorb and take in fluid from its surroundings, and the more fluid that this takes in, the more it can sort of expand and swell, right? And the more negative charges you have, the greater its ability to sort of do that, to sort of pull in and attract fluid into itself and expand and swell. But when the disc degenerates, what happens is it loses a lot of these negative charges. So then that reduces its ability to pull in fluid and swell and expand. And you can see that in this figure here as well, this figure to the right, where as your degenerative rate increases, meaning with increased degeneration, you see a decrease in the overall swelling pressure. And then the same kind of trend can be seen with stiffness here as well. So when the disc is in its healthy state, right, it's pretty stiff, it's rigid, it's kind of hard to compress. But once the disc degenerates, it loses a lot of that stiffness, it loses its rigidity, and it becomes more flexible and more fluid-like. It's easier to compress. And you can sort of see that in this plot here as well. You see a decrease in the stiffness with degeneration. And lastly, I looked at the permeability of the disc. So in its healthy state, it's relatively impermeable because you can kind of see how small these pore sizes are. But when the disc degenerates, and specifically when the collagen network surrounding the nucleus of the disc sort of breaks down, you can sort of imagine how that would open up pores a bit and open up room for more fluid transaction. So so the pore size generally increases with degeneration, opening up permeability and increasing permeability with degeneration. Oh, and this animation just shows how the expansion process works with fixed charge density. But okay, so now moving on to the main results that I have. You basically see a bunch of box plots and some histograms down here, and you can see that regardless of what the condition of your disc is, you see a general increase in your fracture risk as you age over time, which is pretty expected. But the main thing that you should take away, the main key takeaway here, is that if you have a disc that's loaded on top of a vertebra here, and if the disc happens to be degenerated, you actually see a decrease in the amount of pressure and the amount of compression that it transmits to the vertebra, that sits below it, compared to when you have a healthy disc, which actually transmits more pressure and compresses the vertebra more. And this basically shows you the same thing. This is basically a spatial plot of the vertebra. You're looking at the vertebra from a sagittal view here, and basically imagine, having a disc that sits on top of the vertebra down here. And if the disc happens to be healthy, right? Remember what I said about healthy discs and that, they're pretty firm and solid and rigid. If you have something rigid like that, that stands on top of the vertebra, you should expect to see a lot of compression here, particularly near the surface, as well as the middle regions as well, due to because I said that bone mineral density is less near the central regions compared to the sides and the edges. But when it's degenerated, when you have a degenerated disc that sits on top of it, there's not as much compression. So yeah, basically overall, now that we sort of better understand the function and mechanisms and the specific factors that influence these fractures, we hope that this knowledge can feed towards the development of better diagnostic tools that can sort of improve clinical interventions that relate to prediction, treatment, and management of vertebral fractures. Thank you.